welcome everyone to this seminar. It's a great pleasure to introduce Professor Rinat Kashaev from the University of Geneva, who will talk to us today on braided Hopf algebra structures on exterior algebras. Please go ahead with your talk.
Thank you very much. Thank you for introduction, and thank you organizers for invitation to give a talk at this seminar. So I should apologize maybe right away that I don't know if there is anything non-associative will be in my talk. So it will be essentially multilinear algebra, and composition of linear maps is associative. But anyway, maybe Lie algebra somehow will be hidden behind. But essentially everything will be associative. So let me start about with motivation and the outline of my talk. First, I'd like to introduce two basic notions to be used in the talk. So the first notion is an R matrix, so which is an invertible map from tensor square of a vector space to itself, which satisfies so-called Yang-Baxter equation, which is written here. So it's some identity in the tensor cube of the vector space. And most likely you've heard about these objects because it is very often appears both in physics and mathematics. In physics, it's a typically underlying algebraic object of integrable systems, in particular for calculation, for solvable statistical mechanical models in 2 dimensions, and in quantum theory. In mathematics, it is most often is used in low-dimensional topology. One can say that it underlies the relatively new subject of quantum topology. Why quantum? Because it is some linear algebra story, and as we know, quantum theory is linear algebra, but it may be in the infinite dimensional vector spaces, but it is a linear algebra. And the outline of my talk is as follows. So I start from recalling the standard way of producing R matrices from Hopf algebras through Drinfeld theory. Then I will turn to a generalized notion of Hopf algebra, which is called Braided Hopf algebra. And then I will describe somehow new way of producing R matrices from braided Hopf algebras. An approach which I think somehow simpler than the standard approach through Drinfeld construction. And you will see while my talk, so if I have a reason to say so or not. And then the exterior algebra, which is the main subject of my talk today, will appear afterwards. So it is a usual exterior algebra, but with the structure of a braided Hopf algebra, and this structure depends on deformation parameter, which I denote by P, but you can think of it as also as Q. But usually Q in quantum groups, I think, is related as a P squared here. And then I will finish up with some further perspectives. So how we get the R matrices from Hopf algebra? So the standard way is that you start from any Hopf algebra, but you need just one condition for the Hopf algebra, that its antipode is invertible, which means that you should throw away some class of artificial pathological Hopf algebra, so to say. I mean, you can construct a Hopf algebra with non-invertible antipode, but typically in known cases, antipode is always invertible. For example, for finite dimensional Hopf algebras, antipode is just automatically necessarily invertible. And then, so the next step, we construct the quantum double, or the Drinfield's quantum double, which is again another Hopf algebra, but it is a bigger Hopf algebra because as a vector space, it is a tensor product of the input Hopf algebra and its dual. And the remarkable thing about the quantum double is that it has a so-called universal R matrix, which is if you think of a finite dimensional input Hopf algebra, then Drinfeld double will be again finite dimensional, and then there will be an element in here which will satisfy the Yang-Baxter equation in some algebraic sense. But if the input Hopf algebra is not finite dimensional, it is not a problem. In principle, D of H still well defined. The universal R matrix is less well defined, but you can make it well defined, for example, by going to dual of the quantum double. Then in that case, this element will be replaced by bilinear form on the dual quantum double. And it doesn't matter after that if the algebra is finite dimensional or not, because the bilinear form is well defined irrespectively to finiteness of the dimension of the algebra. And then the next step, we pick a finite dimensional representation of the quantum double, and then we evaluate the universal R matrix on that chosen finite dimensional representation to end up with a R matrix in the sense which I defined in the beginning. So this is a standard approach. And for example, if you take one of the simplest quantum groups, if you take a Borel subalgebra of UQSL2, which is written here as a presentation, so two generators, one invertible and group-like, and another one is skew primitive, and then you make all these steps. Then you will end up with for any positive integer n, there will be unique up to equivalence n-dimensional representation of this algebra, and the resulting R matrix through application in quantum topology will correspond to n-colored zones polynomial. So that is a standard known approach to construction of R matrices. And the goal of my talk is to use somehow a different approach, which is based on the notion of braided Hopf algebra, which is a notion which naturally generalizes the notion of a usual Hopf algebra. So let me just briefly explain what it is about. So first, we introduce the notion of a braided vector space, which is just a pair of a vector space and a solution of the Yang-Baxter equation on it. And then what is a braided Hopf algebra? It is a braided vector space, but endowed with 5 extra morphisms called product, unit, co-unit, antipode, as for usual Hopf algebra, which still satisfy the usual Hopf algebra axioms, but in a braided category. And this means that there is one relation which will be different from the usual Hopf algebra, namely the one which contains the symmetry relation in the usual vector space category, where in the braided vector space category it will be non-trivial braiding. So here it is this the compatibility relation between product and coproduct. So in the next slide, I will give a list of graphical string diagrams for description of all these structure maps. So here they are. This is symmetry. This is a product. So you should think of each vertical line corresponds to a copy of the vector space H. And if they are next to each other, then it means that we take a tensor product for each line. And then the maps act from bottom to top. For example, this tau acts from H tensor H to H tensor H. And likewise for other maps, for example, product acts from H tensor H to H, coproduct other way around from H to H tensor H, unit, yes, so the scalars are mapped, correspond to empty line. So this is why the unit, if we recall that unit should be a map from the base field to Hopf algebra. So this part is nothing, and then the result of the map is H. By duality, this is the co-unit and the antipode. And then the axioms, so associativity, unitality for the product, co-associativity for the coproduct, co-unitality for the co-unit, and the properties of the antipode. And here is a compatibility between the product and coproduct. And as you see here, the braiding interferes into this relation. And this is the only relation which makes usual Hopf algebras different from more general braided Hopf algebras. But in braided case, we should complete this list of properties with the properties that all morphisms are morphisms of the braided category, which means that so that the unit should pass freely through a braiding map. In this case, is likewise for the co-unit, likewise for the antipode. And then same thing for product. For example, this is a property that the coproduct passes freely through the braiding in natural way from two sides, or up strand and the lower strand, and the coproduct as well. So here is a complete list of all properties of a braided Hopf algebra. And as a remark, I can say that, for example, if you know that you have a braided Hopf algebra, then with the complicated braiding, as it will be the case later on in this talk, then you can express the braiding map entirely in terms of the structural maps of the Hopf, braided Hopf algebra. So you see here the number of coproducts, 3 coproducts actually, 3 copies of products, 2 copies of the antipode, and the composition corresponding to this diagram. And this is nothing else but the braiding map. And for example, if you have a candidate for a braided Hopf algebra where you know product, coproduct, and antipodes, then you can just check if it is indeed braided Hopf algebra just by taking this composition and verifying if it satisfies Yang-Baxter equation, for example, For example, if it doesn't satisfy Yang-Baxter equation, then no, your structural constant do not correspond to Braided Hopf algebra. Okay, and another remark is here where it corresponds to diagrammatic equation of this form, which means that the antipode of the product. So if you take two elements, take the product and apply the antipode, then the result can be calculated in terms of antipodes of the elements which you multiply, but modified by using the braiding in particular in this way. Okay, so let me give a class of examples of a very general class of examples of braided Hopf algebras. So you start from a braided vector space, which means that you just solve Yang-Baxter equation. And then what you do, you take the tensor algebra of this vector space, which is the infinite dimensional direct product of tensor powers of the vector space V, where the product is just a tensor product. And then you can promote this algebra to a braided Hopf algebra by declaring that all elements of the vector space V, which correspond to degree 1 elements, to be primitive. Primitive means that delta of x is x tensor 1 plus 1 tensor x. Primitive. So all elements of V have a coproduct of this form. And then all the other coproducts you calculate using the compatibility relation here. So for example, if you want to calculate the coproduct of two elements, then you proceed with the left-hand side of this equality. And you will have a coproducts over lower degree elements. Okay, so this way you induce braiding. Of course, you do, for example, for degree 2 elements, you will have this kind of braiding composed of braiding of degree 1 elements, and so on. So you this way you induce braiding on the total underlying vector space of the tensor algebra. So this way you get a braided Hopf algebra, and you can go by quotiening this Hopf algebra with respect to maximal Hopf ideal. In this case, this quotient braided Hopf algebra is called the Nichols algebra. So in concrete terms, this maximal Hopf ideal is generated by primitive elements of degree 2 and higher. So of course, all degree 1 elements are primitive, but you don't touch them because this way you will kill part of your input vector space. So this is why you try to kill only the high degree primitive elements. And now, what is the construction of R matrices from braided Hopf algebras? So, so the only thing, the extra ingredient we need is an automorphism. So you pick an automorphism of your braided Hopf algebra, and then immediately you have an R matrix on the underlying vector space of your braided Hopf algebra. And the definition is pictorial, given here. So phi is an automorphism. And here you have a 3-valent vertex, which is defined this way. So you see you apply coproduct to the second argument here. Then you apply the braiding. Then you apply the composition of the automorphism and the antipode, and then they take a product of all three components. So this is the lambda R, which is actually is a algebra action from the right. And then here is the example how this construction works. In the simplest case, let us take the polynomial algebra where the input vector space is one-dimensional. In this construction, we take a one-dimensional vector space with the braiding input. This is the basis element of the of this one-dimensional vector space, and then braiding is given by a non-zero parameter Q. So basically, we don't have choice, right? If you have a one-dimensional vector space, then the tensor square is one-dimensional. So any linear map is just one scalar. But we take as the automorphism a diagonal automorphism, which scales the basis element by integer power. So sorry. So here this should be x power n, right? The basis element, because no, sorry. I think it is correct actually. So you just take you on this generating element, you define the automorphism by this integer power of parameter q, integer negative power. And then what happens? So a priori, this R matrix is infinite dimensional because the polynomial algebra is infinite dimensional. But as a matter of fact, due to this choice of the automorphism, the finite n-dimensional, n+1 dimensional vector subspace given by monomials x to I with I from 0 up to n is an invariant space for this R matrix. So and in this way, we get a R matrix acting in the dimension n+1, so which reproduces n+1 colored Jones polynomial. So saying differently, this input data is equivalent to the input data of UQ SL2. And as you see, it is very economical in the sense that nothing sophisticated is put as an input here, just a one-dimensional vector space and one parameter for exchanging the basis elements. And basically, this was the main motivation for us to push this construction to more complicated cases to see how what kind of R matrices we can get. And now I'm turning to the main topic of my talk. So and here is the main result, which states the following. So we take as an input a braided vector space V with ordered basis. Okay, so the vector space comes with a linearly ordered basis. And with respect to linearly ordered basis, we define a solution of Yang-Baxter equation given by this formula. So there is a free parameter, P, non-zero deformation parameter P. Theta is a Heaviside function, which says if A strictly bigger than B, if first argument is strictly bigger than B with respect to this linear ordering of the basis elements. So in this case, it takes value 1, otherwise it takes value 0. And that is it. So this formula is valid for any pair of basis elements which form a basis of the tensor square of V. So this is the input braided vector space, and then at the output we state that the associated Nichols algebra. So we take as before. We take a tensor algebra, look for maximal Hopf ideal, and then after quotiening as an algebra, this becomes isomorphic to exterior algebra of vector space V. In particular, for finite dimensional V, it will be finite dimensional algebra. But it is a braided Hopf algebra where the coproduct and as well as the braiding and antipode depend on this parameter P. So this is why we denote it lambda P of V. And as I mentioned, so by definition, all elements of V are primitive. And the braiding on the whole vector space of the exterior power is induced by this input braiding. Yeah, so this is a main theorem, and in the rest of my talk, I will be working with this braided Hopf algebra. And in particular, I will now describe the set theoretic basis of it. But set theoretic basis, it is just a standard basis. So if you have a basis of vector space V, then you just take wedge products of basis elements of V to create the basis elements of the exterior algebra. But since we have a distinguished basis for V with linear order, so we use them to cook up basis elements of the Hopf algebra. So this is a notation for size k subsets of the set B, of the basis of V. So P, this is a power subset of finite subsets of B. So this is a subset of in power set of B, but we consider only finite subsets. And so as you see, I don't assume that V or vector space V be finite dimensional at this moment. Even infinite dimensional vector space, the construction works perfectly. So we consider so these are degree K exterior powers. And this is a notation for those exterior powers. So, but this should be thought as also like in the more standard notation, like this. But I suppress the wedge to simplify notation. The only thing we care about is that we order them according to their natural order. And then we can describe the structural maps of the Hopf algebra. So before doing this, so let me just extend the Heaviside symbol to subsets, actually finite subsets of B, just by summing over corresponding subsets of the initial Heaviside function. Gamma k will denote always this particular function of integer k. And then we have, for example, for exterior product, of course, this is a standard exterior product of basis elements. So it vanishes unless the corresponding subsets E and F are disjoint. If they are disjoint, then we just put a union of them up to some sign. And this sign is controlled by this function. Because remember that we have to put in the global order all the basis elements which enter in these subsets E and F. So this is why a sign comes out. And the coproduct is kind of similar, but as you see, this deformation parameter enters explicitly. But otherwise, if you put p equal 1, then this will be just dualized version of the exterior product. So in particular for p equal 1, we have the standard super Hopf algebra structure on the exterior algebra, which is well known to come from as a Nichols algebra corresponding to Z mod 2 grading of the vector space. And the antipode is given in terms of this function, where mod this notation stands just for the size of the finite set E. Next thing is braiding in this Hopf algebra, and this braiding is more or less is the same thing as a famous MOI calculus. MOI stands for Murakami Ozuki Yamada. So there's something they invented in the framework of UQSL2 quantum group. And there is no wonder in principle that MOI calculus shows up, because the input braiding tau p, which I defined here, is more or less is a twisted version of the fundamental UQSLN R matrix. But why twisted? Because as an algebra, the corresponding Nichols algebra is non-deformed exterior algebra, while with non-twisted R matrix, it will be Q-deformed version of the exterior algebra. And then, so the braiding is given by this explicit formula, which is a known formula in MOI calculus, originally due to Murakami Ozuki Yamada back in 1998. And subsequently, the same formula was reproduced by Kautis, Kamnitzer, Morrison in 2014. So we have, but of course, this front numerical factor in the sum differs from the formulas of Murakami Ozuki Yamada and Kautis, Kamnitzer, Morrison, because their case corresponds to untwisted UQGLN algebra, which means that their exterior algebra is a Q-deformed exterior algebra. And as a result, so in explicit form, the formulas will not be structurally will be similar, but not literally. In particular, this function is different in their case, in our case. And what is special in our case is that we can provide a new proof, which is based on this explicit formula for the braiding in terms of structural constants of the Hopf algebra, something which wasn't known originally. And so the proof, I don't know. I'm not sure that I've seen the explicit detailed proof of the formula. So the answer is written in those papers, but to my understanding, there are no many details of derivation, simply because it is a rather complicated derivation. And in our case, it is not very simple to derive, but as a starting point, this equality is very useful. And but we can go further, and so we can calculate matrix coefficients of this braiding, which means that we can evaluate each coefficient with respect to set theoretic basis of the exterior algebra. And to describe this answer, so let me just go a little bit into Venn diagrammatic set theory. So assume that we have 4 finite sets. So everything lives in is a subset of the basis. And but we assume that so E and F are arbitrary, but we assume that G is a subset of the complement of F in E, and similarly H is a subset in the complement of E in F. And here is a Venn diagram for that. So we have E, F, they intersect somewhere. But the important thing, G should be in this part. And likewise, H should be in this part. That's a condition. And then we define C as an intersection of 2 sets. Then we define E dot, the complement in this complement of G. So this bright green part of the diagram. Likewise for F dot, bright yellow part here. And then we define a number associated to these 4 subsets, some sign. Yeah, and the primes. So the primes are given here. So what we do, we remove G from E. So here is E. So we remove G and replace it by H. So that in the complement of G of E, we adjoin this part of H. That's we call E prime. And symmetrically for F, so we remove H part of F and adjoin G part to the result. So this is called a F prime. And now we have a function, a number associated to it, so that some sign coming from Fe and the F prime E prime, then some power of P, which comes from E, G union C, so here, and the F dot, something non-symmetric at all, and E prime. So this is a multiplicative factor. And then there is a product part, which is the product of binomials. So some power, so the product goes over the elements of G, right? So this here I'm using the subset notation. So it's a size 1 subsets of G. So this is the multiplication variable. And then we take a power of P given by theta function in terms of A and H. So this one element subset, and roughly it counts, I mean, it is either 1 or 0, depending if there are elements of H strictly less than the corresponding element of G. And minus same thing with the second argument G. So we just compare this element A with strictly less elements. So this contributes positive integer only in those cases. Subtract 1 and take product over all A's. So this is a function beta. And then the first result is that, so if we act by induced braiding over basis elements FE tensor FF, then the result sum over all possibilities of this configuration. So sum effectively is over G and H. So sorry. So well, here I can add the G and the H. So which should run over subsets of those complements times this numerical coefficient, and then this is the explicit form of the R matrix. So which is a more detailed formula than this formula here, because because here the structure of this Moy diagram is not specified. You need the evaluation of it by specifying the basis elements at the input and the basis elements as the output. So this is first result on matrix coefficients, and then the second result is concerned now the R matrix. So remember that just a side remark concerning this braiding. Of course, when you specify the degree of exterior elements, then they are preserved. So this n goes through so the crossing to the other side, and likewise for m. So you see mn here, k here you have summation over k. Then here enters n minus k. So at the output you have here degree n, and likewise so here m minus k. Then m plus n minus k, and then when you remove n minus k, so what remains m here. So you see that there is a degree preserving property, and this means that as an R matrix in a big vector space drawn here, so it has many irreducible sub-R matrices corresponding to each choice of degrees m and n. So this tau hat is a highly reducible R matrix with many irreducible components. But now, if we go to raw R matrix, which depends on the choice of the automorphism, so we choose automorphism in diagonal way. So it acts on a basis element by just scaling it by some power of new parameter t, new non-zero parameter t, according to this formula. Just to recall you, according to this formula definition. So we obtain now we obtain first the formula for this row. Now you see that the degree is not preserved anymore. So if you put at the input m and n, then at the output the sum of n plus n is preserved, but not individually. So n goes out like I, and then m goes out like m plus n minus I. For all possibilities, of course, I should be less than m plus n to have a positive degree. And then here is a first formula in terms of Moy diagram. So that you have a Moy diagram, very similar to what we have here, but it is more general because now the degree is not preserved strand by strand. So you see, for example, here it k minus I to have I as the output. Here m minus k, and then here m plus n minus k. So you see that at each vertex you have Moy rules for Moy diagrams, but globally this m is not equal to this difference. But still you have same type of coefficient as before for the braiding, but there is a correction term where whole dependence on t is concentrated. So in this part there is no t dependence. And remember that t comes from the automorphism. And as a matter of fact, this R matrix is irreducible. So there are no invariant sub-R matrices for this row. So the whole vector space is involved as a, on which this R matrix acts. And furthermore, we can derive a formula for its matrix coefficients. So we have a similar formula here as before. This is again summation over G and F, G and H, sorry, which are subsets. So the same Venn diagram applies here. So we have still these conditions. But the coefficient denoted R, E, G, F, H is somehow different. The essential part still is given by the same beta function, which I explained here. But there is which is a t independent, but the t dependence is concentrated in this part. Here I'm using the Pochhammer symbol, just in case if you don't know, x comma q n is 1 minus x, 1 minus q n minus 1 x. So that you just keep multiplying x by q to cook up this q Pochhammer symbols. So and this symbol enters here, as you see, but with base p. Yeah. So this is the explicit form of the R matrix. Of course, its size, it acts in the big dimensional vector space, which is dimension of and the p of v, of course, is 2 power dimension of vector space v. It grows very rapidly. In the simplest case, when the dimension of a vector space is 1, then it is so small, the exterior algebra, that P doesn't enter at all into the structure of the algebra. So P is irrelevant for equal for dimension 1. P is irrelevant. But if dimension v equal 2 and higher, then P, of course, enters all around in the structure of the R matrix. And then what we observed by numerical calculations, so if we take a finite dimensional input vector space. Then this row matrix leads to a Links-Gould invariant, which was defined through the standard approach through super quantum groups, namely the UQGL n/1 supergroup. They actually did for NM here, but this construction, which I explained today, corresponds to only one odd generator in the GLN/M algebra, and it corresponds to a specific irreducible representation of the superquantum group of dimension 2 power n. And parameter t enters in the standard approach through the choice of this. There is a continuous family of representations of this given dimension, and this parameter plays the role of parameter t in the Links-Gould invariant. And in our case, it comes through the choice of the automorphism. And I remember that the claim was that in this approach through to construction of R matrices through Braided Hopf algebras and automorphisms, automorphisms somehow play the role of representations in the traditional approach. Okay, so that's it remains a conjectural relationship with the Links-Gould in general, because we checked it only for small values of n given by 2, 3, 4, which are consistent with the result of David. And just to summarize, here the few possible future directions. For example, one important problem in my mind is to learn how to calculate, at least on the level of examples, the not invariance for arbitrary values of n. So this way we can hope to get an invariance depending on the extra variable, where n can be thought as a extra variable. So this way we have in principle three variable not polynomials, because we have p, we have t, and also we have this integer n. So remember, if you take a standard Jones polynomial, for example, then Jones polynomial can be generalized to from one hand side to colored Jones polynomial by considering irreducible representation of UQSL2, but it can be generalized to Hopfli PT polynomial by considering SLN instead of SL2. And then the Hopfli PT polynomial is a most famous two-variable polynomial, where the second variable, which is a priori integer corresponding to the rank of the SLN, it is promoted to a continuous variable. So the Hopfli PT theorem states that so SLN quantum invariants are specializations of true two-variable Hopfli PT polynomial to those discrete values. And in this sense, it is possible that that the calculation for arbitrary n probably can be generalized to non-integer values of n, to look at this n as the extra third variable. And another perspective, of course, to try to understand the colored versions, because this is the analog of the fundamental representation for the UQSL2 Hopf algebra. But the colored Jones polynomial by themselves, they are very interesting, and in particular for n equal 2. Conjecturally, the two-colored version of the Links-Gould polynomial is much more sensitive to the topology of knots. In particular, up to 19 crossing diagrams, it detects the cipher genus of the knot, two-colored version. But while the Links-Gould polynomial itself, which is a one-colored version, it is not that powerful. It cannot distinguish mutations, for example. And the last remark concerns generalization. Can one get the most general version of Links-Gould polynomials to super Hopf quantum groups indexed by two integers? And it is not clear because we are able to treat only m equal 1 case, and if m is a bigger number, then it is not clear what would be the input R matrix in our theorem, because from one hand side the Nichols algebra should still be finite dimensional, which means that the input R matrix should have a very specific properties of having a lot of given eigenvalues, which will allow to create sufficiently many primitive elements in high degrees to get a finite dimensional Hopf algebra as a quotient in the Nichols construction. Okay, I stop here and thank you for your attention.
Thank you very much for your very interesting talk. Are there any questions or comments? And now I have to.
So I don't know if this is a non-associative seminar, so I don't know how R matrix is a common thing for this audience.
Yeah, that might be, but non-associative means, of course, not necessarily associative, right? It doesn't mean it has to be not associative. No, but maybe you're right. And maybe I ask a question, or
Yes.
I mean, on the last slide, the last topic you mentioned, I mean, but you said the Nichols algebra is supposed to be finite dimensional. I mean, could one not use
No.
the
Okay, Nichols algebra is very seldom finite dimensional. Most
then
often
I misunderstood what you said. Yeah, okay.
But to have a finite dimensional Nichols algebra is a kind of luck. You have it's a very rare thing.
Yeah, okay. Then I misunderstood something you said at the end. So could one somehow? I mean, that's just blank speculation. Maybe it's totally stupid what I'm saying. But if one uses instead of the exterior algebra you use as a tensor product of the exterior and a certain kind of symmetric algebra of the vector space, could one in this way maybe get the two?
Yes, this is one idea, but the symmetric part will produce infinite dimensional Nichols algebra.
Yeah. And
like polynomial algebra. Yes, and then of course the R matrix rho will exist, but it will act in infinite dimensional vector space. And then to cook up not invariance, you have to do something with the problem of infinite dimensions, because from infinite dimensional R matrix we don't know how to produce invariance. We really need to be finite dimensional, and then of course, from this infinite dimensional Nichols algebra, the next step is to look for invariant subspaces, where this infinite dimensional R matrix would restrict to a finite dimensional R matrix, like in colored zones, if you remember, I described, because the algebra was an infinite dimensional polynomial, and then we had to carefully choose the automorphism the way that there is a sub-R matrix, finite dimensional sub-R matrix. But I believe that the dimension of the R matrix coming from of Links-Gould R matrix coming from this algebra is just 2 power nm.
Okay. Yeah, that I didn't know, of course. Yeah. Okay.
And then naturally, one would expect to have as a Nichols algebra finite dimensional with this dimension Braided Hopf algebra. And then again, the automorphism will not be restricted. It will be a new parameter. So this is how it would be 2-parameter element. But what is not clear, what one should take as an input R matrix. But it should be Hecke type. It is clear to me. But unfortunately, I'm not aware of what kind of, the classification of Hecke type R matrices. So I think that the more general class of R matrices should sit in this more general Hecke type R matrices.
Okay, yeah, okay. Yeah, thank you. So are there now any questions or comments besides my small one? Yeah, if this is not the case, thank you so much for this very interesting talk.
Thank you for your attention and your question.
Yeah.